Hello and welcome to the second video for this chapter. What's this chapter? Chapter 5. All right, so this is chapter 5 from the Physics of Everyday Phenomena, looking over here at our table of contents. And what did we cover in the first video? Chapters 5.1, rather sections, and 5.2. And now we're leaving off here at 5.3, which leaves us 5.4 and 5.5. All right, all very interconnected, all about planetary motion and getting into some details that really aren't so much about the physics, but really the applied physics or the astronomy, honestly, of, kind of near Earth astronomy, considering the moon, considering the solar system, motions in the solar system. We spend some time on Kepler's laws, which I don't always cover in a physics class, but if you've looked at my YouTube channel, then you know that I also teach a lot of astronomy. This stuff is near and dear to me. That said, since we are in a rather fast-paced physics class, covering a lot in this type of course, a conceptual physics course, well, I'm going to try to move through the background side, the astronomy side, rather quickly, I guess leaving that for an astronomy class, okay? That said, we still have quite a bit to cover, hence trying to move through the background quickly, all right? So if it seems like, background astronomy facts, expect me to go a bit faster. That said, we're going to get to it. So we're going to start off here. It's about 2/3 of the slides, by the way, so it is the majority of the lecture, but hopefully it won't be that much longer than the first video, and I'll see if I need to split the video. So we have planetary motion, right? So the ancient Greeks believed the sun, the moons, the stars, and the planets all revolved around Earth. This isn't because of some conceited view of their own importance. It was just based on common sense that the Earth was fixed in place, and the things that appeared to be moving were in fact moving, okay? It is a big stretch to realize that the Earth is not fixed in place and is actually moving at incredibly fast speeds that we couldn't comprehend in our own atmosphere, because if things move that fast, they burn up, as do incoming asteroids, at kilometers per second speeds, like Earth's orbital speed around the sun. So that's what I mean. It was absolutely a reasonable assumption, okay? And I'm sure we have reasonable assumptions today with our great body of knowledge that if humans are around 5,000 years from now, we'll look back on and they will seem unbelievably simple. Maybe that's just the nature of progressing in this incredibly complex universe. Regardless, this type of view had a name. It was called the Geocentric View. Just means Earth-centered. This is in contrast to the heliocentric view, which we'll talk about. Okay, that just means sun-centered, which is accurate. So this view matched their observations. Okay, absolutely, as I said. Now, as the observations became more refined, the issues did begin to come up. This is very much a nature of science. As we build more ideas, and then we test those ideas, more importantly, and we end up getting these little pieces of data, little complex systems that at first might just be a mistake, might be just a limitation of our ability to measure things because they seem so strange, so out of place. But then if we continue to measure them in those strange little behaviors that we could so easily write off if we don't have the accuracy, end up being important telltale signs that there is something wrong with our model. And it's so interesting that just a little detail ends up being so important. And that's essentially the story that this idea tells here, because when we look at the orbit of, not the orbit, but the motion of Mars through the sky, okay? Mars being a wandering star, right, in ancient terminology, because the exact concept of planets, well, what exactly were they, right? Were they all glowing for the same reason, right? So Mars is of course a terrestrial planet, as we know today. We have many rovers on Mars, but even a helicopter. But besides that, right, so Mars, because it has a nearby orbit, is bright, easily detected, and because it has an orbit that's further from the sun than us, what we see when we easily observe Mars in the night sky, and also we can observe Mars in the night sky in the middle of the night, because we can have cases where we're facing away from the sun. We don't have to worry about catching a glimpse of the planet just before sunrise or just after sunset, which is the case for any of the interior planets, which are Venus and Mercury. But in the case of Mars, as we look out towards Mars, we, in the middle of the night, we notice that its behavior is strange in that it's drifting in one direction over consecutive nights. So as the dates of the year go on, Mars is becoming further and further towards where the sun sets in the west, okay? So it's moving in that same direction gradually, okay? Over any given night, it's going to rise and set with the stars and seem basically motionless over the duration of that night. But there's a noticeable change over many nights, that it doesn't stay fixed relative to the fixed background of distant stars, all stars, right? And so then we end up with a case where Mars is wandering. But then it begins to turn around. This turning around is called retrograde motion. We can see it here in a figure, a bird's eye view of the ecliptic plane, which is just the orbits of the planet around the sun, the planets around the sun, just focusing on a completely not to scale view of Earth and Mars, okay? And then these dots over here, which are very much not to scale, represent light years away instead of just mere astronomical units. So just an incredibly longer scale, right? Tens of thousands of times further. Those are essentially fixed in place. There's no, discernible movement of those stars relative to each other. They appear absolutely motionless to pretty modern telescopes, by the way. So the idea then is that fixed background is then going to place Mars at different locations relative to it. That was the wandering I was referring to. But what about the retrograde part? Well, the retrograde part is because Mars, as I said, drifts backwards. So it doesn't continue its day after day march further towards the west. There is a period of about a month and a half, maybe closer to 2 months, where it actually takes an arc and drifts backwards the other way. Why is that? Well, as this bird's eye picture shows, it's because Earth is passing Mars. Earth, having an interior orbit to Mars's orbit, has a shorter period of orbit. That turns out that's one of Kepler's laws, a direct proportional relationship, not quite a formula, but a good proportional relationship between the period of a planet's orbit around the sun and the distance of that planet from the sun, its radius of orbit, okay? So since Earth has that smaller radius of orbit, that means it has a shorter orbital period. Our year, the Earth year, right? One of our years is shorter than a Martian year, which is called a Martian sol. All right. So the Martian sol is longer, has a longer year. All right. If it has a longer year, right, then you might just say, oh, that's just because it has a bigger loop. But it turns out that it has a significantly longer year because not only does it have a bigger loop to complete, which would just take longer, even if it was moving at the same speed, which it is not, okay, because it's moving slower and has a bigger loop, which means this year is even more longer than it would be if it was just had a larger circumference loop, a larger circumference orbit, right? It's not just a loop, it's an orbit, right, to complete. So, all that said, okay, we have this relationship. Mars is moving slower. We pass it. We're just a faster runner on the inside track, and we pass by Mars. And as we do it, our view of Mars relative to the background, we see it drift backwards. Otherwise, it's drifting the other way. Why? Well, think about every other time except when we're immediately passing it, right? In those cases, it's always just going to be further in that same direction. It's going to be drifting, right, towards the west, except right at that point where our line of sight makes it appear to drift backwards because we're passing it on our interior orbit. Okay, so that's called retrograde motion. It's often called apparent retrograde motion because Mars is not literally moving the other way. And so technically retrograde motion means the other way. That term is often used because all of the planets orbit around the sun in the same direction. They all orbit as viewed from above the ecliptic plane, which is to say, our North Pole approximately, besides our axial tilt, but continuing up from our North Pole, looking down on the solar system, then all the planets go counterclockwise, right? They all have a counterclockwise orbit, every single one of them, and that's just called prograde motion as opposed to retrograde, and it's the normal motion of the solar system. Okay. And that counterclockwise, that idea that everything's moving in the same direction, we see that on the scale of the galaxy as well. It comes down to conservation of momentum, okay? Because there's only one direction that is inevitably going to win out. You can't keep all the directions over many series of collisions. There's always going to be one that just from random chance there is more moving in that direction to start with, and that direction eventually will prevail until it's the only direction, okay? Because think about all the collisions. You can't keep the whole system just going in every direction over time, okay? So All that said is there's one prograde direction. Retrograde is the other way. Mars appears to go the other way because we're passing it, okay? So back to the ancients real fast. They had to explain that. That's that little detail I was talking about. That's a little wrinkle that you could say, oh, it's just an error in our measurement. But if it's not, which it wasn't, then what's going on? Okay, and in this case, it's pretty significant. It's really obvious, actually, many degrees of motion over many days that Mars is drifting backwards. But still, I mean, it's just a little detail, right? Otherwise, everything else makes sense. And there's so many other reasons to reject the idea that Earth is in motion. Like how could we be standing on a planet, right? And what does that even mean, right? Did they understand that it was a planet, that it was a sphere, right? How do you come to that conclusion? There's some hints, that certainly ancients could put together, connect the dots. They could follow those hints. They could kind of ascertain that Earth was spherical for a number of reasons, including ancient experiments performed, before the Common Era. In ancient Egypt, Eratosthenes did experiments of shadows to suggest that these shadows have different angles in the distance, suggests that the planet is this size, right? And it has to be a sphere. It has to have this curvature to it. And furthermore, when you look at a lunar eclipse, and you can actually see that the shadow that the moon casts on the moon, right? The moon casts on the moon. The shadow that the Earth casts on the moon during a lunar eclipse, because the lunar eclipse is when the moon is in the Earth's shadow, as opposed to a solar eclipse when the Earth is in the moon shadow. So the moon is between us and the sun, and it's casting a much smaller shadow. But the moon completely gets engulfed in our shadow. And in that case, you can actually see when the moon comes out of our shadow, a curvature to it, right? Why would our planet be casting a curved shadow if it wasn't, a ball, for example, So regardless of that, whether we lived on a ball or not, it sure made a lot more sense that that ball was motionless, not flying kilometers per second, which the math demanded, right? Even if you thought about the distances, right? So it's so fascinating, right? That this incredibly unintuitive, right? At first, at least, reality that we live in, was missed by so many great minds over so many centuries, right? But of course, eventually the technology rapidly it became good enough that we could confirm measurements and make measurements, and we've been doing that for approximately the last 500 years, right, in human history. So since they didn't think Earth was moving, how the heck does Mars drift backwards? Well, the idea was that Mars had to be on a separate little, almost like a gear. Imagine the solar system is a bunch of large gears, and there's gears on gears, like some clockwork machine. Or it's just some sort of magical or divine creation where Mars is spinning around some empty circle, right? There's nothing there, because there's nothing we see, at least, nothing that is shining. And so there's just something that is invisible that's keeping Mars spinning around a little circle, a fixed point called an epicircle, all right? Or it's the center of the epicircle, or maybe an epicenter. Totally fictional concept, but it does explain that type of motion, okay? So interesting, right? So there was a kind of a mathematical, like, hey, let's piece things together, right? Come up with a model that works. It explained the behavior, right? But it wasn't the right model. Turns out it was, completely wrong. It was based on a wrong premise, right? So that certainly is something to consider when, as you're following the scientific method. And also, it wasn't the simplest model. Maybe it was at the time, in all fairness, but if another model comes along and it makes the same, or explains the same phenomenon, matches the same behavior, tracking Mars's motion, and it is a simpler model, then that's the one that you should pursue more seriously and test, right? It's the idea that the simplest model is more likely to be correct, right? It's going to be getting to the truth. And physics is always trying to do that, always trying to delve down to the simplest and smallest number of building blocks, right? Not having any redundancy, right? And not coming up with wild, crazy explanations just because they happen to match the observations. Okay? So, correction, right? Starting with Copernicus, and this revolution in science happening just about a generation and a half before Newton. We had the birth of the heliocentric model in the modern world, right? Careful astronomical observations were needed to determine right what was accurate. Tycho Brahe is well known for coming up with a mapping of the solar system at the right time when that data was so crucial. His assistant Kepler then used that data to really kickstart the the science of astronomy. Okay, so Copernicus was so important and was a key character of a generation before Kepler, at a time when it didn't seem like science had got to the level that it did with Kepler. There seems to be in those intervening 50 years or so just a flourishing of mathematics, a formalizing of the way that ideas were presented, and that was kind of the key, because then one person's findings could be easily passed to another, and you started having great minds working together. And so Kepler was at the beginning of that. And his 3 laws, which became widely published and then disseminated, were all about planetary orbits. Okay? So one of his laws, his first law, was that he was able to show, with a really interesting step here, that not only was the heliocentric model the only one that was going to work, right? Because otherwise you didn't have the most simple model. You couldn't base the whole set of observations off just a few set principles. Furthermore, he noticed that the orbits weren't quite circular. So he was really working out the math, right? Fitting the data points, matching the exact equations of the circle, to where we were making the observations on Earth, relative to what were the different radii relative to the sun, right? The actual center. Imagine calculating it all out, making all those calculations, because you're a moving observer, moving of all these planets, and you're just observing those in your local sky, right? Tracking their location at certain times of the night, and then actually calculating it out to a map, right? That's something like a bird's eye view of the planets. So in that process, though, he was doing it so accurately that he realized that it was hard for him to accept that they weren't circles, right? Because that was actually an idea that he had just taken to heart and had assumed. And so there's some interesting, famous, often quoted words from maybe a preface to his publication, and what it said was that if it hadn't been there, if he hadn't measured it over and over again and really felt that the number was right, he would never have pursued the possibility of elliptical orbits, because it just didn't sit well with him. But it ended up being absolutely accurate. Now, to be fair, in our solar system, we actually have fairly circular orbits of most of the planets, which, by the way, is actually unusual. It's not unheard of, but as we've studied other solar systems, it's fairly unusual. There's a lot of much more elliptical orbits of planets. Now, there are bodies in our solar system that have elliptical orbits, comets, asteroids, especially comets, by the way, very highly elliptical orbits, which means really stretched out. That means large eccentricity. But most of the planets are pretty close to perfect circles, even the distant ones like Uranus and Neptune. Less so of Pluto, but still not too far off. In fact, the only planet that has a fairly elliptical orbit, which means an eccentricity that isn't approximately 0, because 0 eccentricity, that's a circle. It's a subset of an ellipse, but it's called 0 eccentricity, because the two, as you can see in the figure, the two foci, which is the plural focus, they overlap on top of each other. So that means that there's only one radius. Well, that's a circle, right? You can go all the way around. Whereas an ellipse doesn't just have one radius, it has a shorter side called the semi-minor axis, measured relative from the center, and then a longer side called the semi-major axis. So the bigger the difference, like a really short semi-minor and a really long semi-major, means a really stretched out, highly eccentric ellipse, okay? Well, anyway, one without any stretching, that's a circle, okay? And the only planet that doesn't have a nearly circular orbit is, in fact, Mercury. As it's not super eccentric, but it actually is quite measurably so. Okay? So Kepler's second law continued with that idea, because for those comets, and which were a hot topic and always have been for astronomical study, because it's such an interesting phenomenon that the way comets swoop in from way out in the distant solar system, and when they come in, they obviously move faster, besides interesting behavior like starting to melt and creating big plumes that follow them as tails, reflecting a lot of light. So all that said, that Kepler then got interested in this idea that with those elliptical orbits, that meant that a planet or any celestial body like a comet is going to be moving faster during the part of the orbit where it's closer to the sun, right? And slower during the part of the orbit when it's further away. So look at the picture here, right? So the idea is that there should be some equal something, right, that takes 25 days when the planet is moving faster, right, say planet. And then over here, where the planet's moving slower, look, it covers less of its overall orbit, but in the same amount of time because it's moving slower. So this idea, actually, that it moves faster when it's closer to the sun and when it moves slower when it's further away, is exactly consistent with what we'll talk about in the next chapter, which is conservation of energy. Okay? It really is. I mean, you can come at it from conservation of energy, but these laws of Kepler predate that. Okay? So what Kepler saw and was able to show mathematically was that the area, right, this sort of wedge-shaped area, is equal in the two cases as long as the time is equal. Right? So whatever time you let the planet sweep out an area, you know, as I said, wedge-shaped, measured from the planet to the center of the sun, well, then you're going to get those two shaded blue areas in this case, very different shaped wedges, one long and narrow, the other one short and stout. Well, those two different wedges are exactly equal in area. Okay? So that's what the law said, which can be paraphrased as just saying that, you know, that the planets go faster. The comet goes faster when it's closer to the sun, and it goes slower when it's further away. Okay? But this shows exactly how much faster and how much slower. Although practically measuring areas is tough. Okay? Now, the third law is the most famous of his laws. It's the one we're actually come back to in a minute. And because it's kind of the most profound, the most kind of just wow, this is something new, right? In that sense, it's a profoundly new law. And it's one you can absolutely numerically test. Okay? So here the law is presented as a proportionality. That is how Kepler thought about it. Now, interestingly, if you set the proportions to be those of our solar system, in that if you set t to be the period, because t represents period, okay? I won't get ahead of myself. T is the period of the orbit. That's the time for the planet to complete an orbit. And we're just talking about planets here, okay? So then t is going to be set. If you want to, kind of use this in an equation, I'll explain, kind of the limited way you can do that, then you can just set t equal to 1 astronomical unit. Now, an astronomical unit is about 149 million kilometers, and it's Earth's average distance from the sun. We say average distance because Earth's orbit around the sun is not a perfect circle, right? But it's pretty close to one, right? Regardless, that value, right, I'm sorry, that's not t, right? That value, the radius, the distance from the sun to the Earth, is the radius, which is r. T, well, that's just 1 year, okay? So those are the two values, okay? So you have r as 1 astronomical unit. You don't actually want to put in those kilometers. It's great to know, right? I want to point out that it's not some weird value, right? It's just 149 million kilometers. But here we're just going to call it 1, right? So we're going to set r equal to 1 astronomical unit, and then set t equal to 1 Earth year. Well, if you do that, right, if you just set them equal to each other, then you have not an equation, because certainly years, years squared, right, the units of years squared are not equal to the units of, astronomical units, which is some multiple of meters, right? So in other words, seconds, right, because there's so many seconds in a year, right, seconds squared are not equal to meters cubed, plain and simple, right? Every equation in physics isn't just numerically equal, it also has to be equal to units. There has to be equal units on each side of the equation. There's no way this is ever going to be an equation as written, right? But it's a numerically useful proportionality if you just plug in multiples of Earth year and multiples of Earth radius, orbital radius. Because think about it. That means that if you know t for Mars, then you know how far away Mars is. You can confirm that measurement. If you know how long it takes Neptune to orbit the sun, then you can just plug that value in Earth years, about 140 by the way. So you plug in 140 Earth years and just solve for the radius. The value you get will be in astronomical units, in other words, a multiple of Earth's radius, but that Earth's orbital radius, not the planet's radius. But that's what you want, right? That's the way the proportionality will work. Okay, so that's Kepler's third law. And the reason I'm making a big deal about it, working as multiples of Earth years and Earth radius, is because that's all it can do, right, as written. And because I'll show that with simply combining it with the very next thing we're going to see, which is Newton's law of universal gravitation, okay, then we actually can turn it into an equation. We can turn Kepler's third law into an equation, rather simply, okay? But so far it's proportionality, and it came first, okay? These are Kepler's laws, foundational understanding of motion in the solar system. And I know you might be thinking, oh, is this an astronomy class, right? But it's just because this is the natural application of it, and it's just how people were progressing the science of the early science of physics. Okay? Now, the thing is, now comes along Newton, right? Besides really kind of formalizing calculus and mostly writing it, and making so many other breakthroughs in terms of just understanding motion, from the very foundational building blocks, Newton also really officially defined what gravity was. Came up with an equation, and interestingly, came up with this like modern standard of equations. Because in a sense, when we look at Kepler's third law, what I see, having studied this a lot and taught it a lot, what I see is this kind of progression, this point where science had was getting incredibly accurate and incredibly math-based, and formalizing, as I said, formalizing this publication process and sharing ideas, but the level of what was kind of the finished product, it wasn't really refined yet. So here Kepler ended up with a proportionality and was done, right? And I don't know if he just kind of washed his hands and said, okay, I'm done with it, this is good enough, or if that was just kind of the culture of at the time. So when I think of kind of what the big idea of one of kind of Newton's contributions, right? Kind of this this great mind sort of pushing the limits, and then people responding to those limits being pushed, right? Because it's what one person does only matters maybe because of the ripples it creates in the overall community of people, right? So, but what Newton did is he pushed the level, pushed the benchmark of what is kind of this modern equation. What's a way that we actually understand something, and what's a law, and you see that with Newton's second law of motion, F equals ma, right? Because that gives us a direct proportionality, right? We've got force, right? We've got mass, we've got acceleration. Mass is the proportionality. The units of mass, relate those two quantities, the pushing and the pulling, and which is the force, and the change in velocity, which is the acceleration, right? Change in velocity over time. And so that defines what mass is. But what's interesting is it defined what mass is where mass was already a natural concept to want to define. But what Newton does with his law of universal gravitation, what I'm about to show you, is he came up with this idea of a proportionality constant, which really set the standard. We see this in physics, the study of physics, the history of physics, and you'll see it as throughout this class if you pay attention to it, that as we introduce a lot of other laws, fundamental laws like Coulomb's law, which is the fundamental electrostatic force, as we look at even things like Ohm's law and all the ways that we just, we express circuits, we see, again, proportionality constants over and over again. We see a way of relating two ideas and having a constant that relates them, okay? So, Newton recognized the similarity between the motions of projectiles on Earth and the moon above, okay? And he said if it's the same force that governs everything, and we know how far away the moon is, then we can actually quantify this, okay? So, he said, okay, then if the moon is just a projectile that's moving so fast that it never hits the ground, then how fast does it have to be moving? And how far away is it? And does that match with the way things behave on Earth? Because he came up with this idea that, okay, yeah, everything falls at the same rate. Acceleration is universal on the surface of Earth, okay? And that was so interesting is Galileo had come up with that idea exactly a generation earlier. Like Galileo died on the year that Newton was born. So that idea was out there, that acceleration was constant. It didn't change over the entire surface of Earth. And that a lot of people were probably thinking that probably had something to do with Earth, right? Earth was pulling on everything at the same rate. But then to extend that to say that Earth's also pulling on the moon is literally in free fall, but it's just moving so fast to the side that it never hits the ground, right? Like here, imagining an unbelievably tall mountain at the North Pole and launching things off that mountain until you eventually launch something so fast that it just never hits the ground, okay? That's all a satellite is, whether natural or man-made, okay? And that's what the moon is, being a natural satellite. Right? Just a fast-moving projectile that's moving fast enough it never hits the ground, and is further enough away, by the way, that the gravitational acceleration that it feels, and thus the centripetal force that it feels, to bring it back to the content from the first video from this lecture, that force is significantly smaller than it would be if it was, of course, as close to the surface of Earth as we are. Okay? So you couldn't maintain the moon's orbit if the moon was much closer, not just because of the, it rubbing against the atmosphere or something, just because you'd end up with a case there where it'd be going the wrong speed, okay? The speed is dependent on the force of gravity. The force of gravity decreases with the distance. How does it decrease with distance, right? Well, the measurements of the moon allowed for Newton to come up with that actual rate of decrease. He was able to quantify the constant, the proportionality constant I was talking about, okay? So what he was able to do is he was able to explain Kepler's first and third laws by assuming the gravitational force between planets and the suns fall as the inverse square of distance, right? So he kept looking at the numbers and seeing what was the mathematical relationship that worked. Well, it turned out it wasn't 1 over r, right? It was 1 over r squared. It wasn't 1 over r cubed either. It wasn't 1 over the square root of r. It was 1 over r squared, right? And so that told him something, right? Now, that also begs the question, where does that come from? Why is it that relationship? But it's still a high benchmark of actually establishing a law, right? With a law, you can plug in the numbers. A law where G is a numerical value, okay? I'll give you the numerical value at the end of the slides, in just a few slides, okay? But G has a particular value. Actually ends up being a small value, and by far it's the smallest value of all the force laws because, gravity is by far the weakest force. By far. Of all the fundamental forces, there's 4 of them, not 5, 4 of them, in the entire universe, gravity is by far the weakest. Which is interesting because it sure seems to dominate the behavior of planets and things, right? Why is that, right? Well, good idea to think about, okay? So that value, by the way, which the G, the constant, right, uppercase G, which I'll give you the value of in a minute, is known as the universal gravitational constant, okay? So the equation then tells us that the gravitational force is equal to that constant times the product of the masses, right? Because he found out that it wasn't just proportional to the, this inverse distance, it also had to be related to this idea, a multiplying together of masses, okay? Which then we see that since the force of gravity is dependent on not just, say, M1 is Earth, and M2 being anything else, like the moon, for example, it also shows that that's why everything experiences the same acceleration as long as r is the same, right? So the moon doesn't experience the same acceleration, as I was saying, but because it has a different distance from the center of the Earth than everything on the surface of the Earth does. But everything on the surface of the Earth has the same r. Therefore, if you were to look at this equation, you'd see then that the only thing that the force is dependent on is the actual mass of the thing, okay? So that means the gravitational force is different for everything. And it differs precisely by multiplying them by the mass of that thing. So that means that we all have our own custom gravitational force, which is dependent on exactly how massive we are, which is why we all accelerate in a vacuum at exactly the same rate. Interesting, right? Well, custom gravity, but shared acceleration. So let's do a quick question. 3 equal masses are located as shown. What is the direction of the total force acting on M2? Okay? So you want to consider the universal law. I'll give you one important fact that I haven't presented is that gravity, you might think, oh, that's obvious. Gravity is always an attractive force, okay? So mass attracts other mass. The moon pulls on the Earth pulls on the moon. The Earth obviously all pulls on us, right? We pull back on the Earth, but not enough for the Earth to notice, okay? So always an attractive force, gravity, right? No questions there, okay? So with that in mind, thinking about the situation, 3 equal masses, obviously the middle mass is closer to M1, so what do you think is gonna happen then, right? Where is the direction of the total force, which is, in other words, the net force? You can place the word total of net, okay? All right, got your answers? All right, let's check. All right, well, it's definitely going to be towards the left because the fact that M2 is closer to M1 really matters, especially because all the masses are equal. Being closer means a much greater force. You half the distance, you get 4 times the force. Why? Because the square relationship, right? It's the same idea. If something is twice as far away, then it's going to be 1/4 the force. If it's 3 times as far away, it's going to be 1/9 the force. It's a squared relationship. Okay, it's just an inverse squared relationship. So things as they get further, as they get bigger, the force gets smaller, quite a bit smaller. Okay. So this type of inverse squared relationship, it's really important. I feel like it's kind of easy to miss the importance of it because it happens just naturally in a lot of phenomena. Right? It happens with spray paint. If you spray paint, right, it sprays out and has to spread out over kind of this like sphere of area, right? Because that's how it spreads. Well, that's interesting because the idea of spraying out and spreading, and kind of like how you would, if you increase your distance from a surface that you're spray painting, you're going to get not a decrease that matches how far you've gone in terms of the coverage, in terms of the density of the spray. So you go twice as far away from the wall, you notice that the spray paint is not, half as faint, it's much fainter. In fact, it should be about 1/4, as I guess 1/4 as dense as it was before, right? So it's like 4 times fainter because it also has an inverse square relationship. Anything that has to spread its influence out over a spreading kind of surface area of effect has an inverse square relationship. Sound does. The effects of anything that's a field, which is a physical term and that applies to electricity and magnetism, as well as nuclear forces. Many of those, actually not all of them, many of them spread, especially the nuclear forces, don't quite follow this phenomenon. But all the macroscopic forces follow this inverse square relationship. Okay, so it's very common. Intensity of light does it, intensity of sound as well. But then both, electric forces, Coulomb force in particular, and here the universal gravitational force. Okay, so since it's this kind of reoccurring, kind of just natural thing that comes up, it's good to point it out. All right. So let's take a look at the next slide. So here is just kind of really illustrating what it means for gravity to always be an attractive force. Okay, so here are two masses. They could be anything. They could be two asteroids or something. We'll plug in the numbers in the case of these in just a minute. We're almost to the last slide here. We'll do some numerical calculations. And so it shows, right, so as if you know both the masses, for example, if you know the mass of the moon and the mass of the Earth, right, we can imagine, M1 is the moon, M2 is the Earth, sure, right? Then you just plug into the equation, M1 times M2, their distance between them, whatever that may be. Maybe that's 300,000 kilometers, maybe it's 30 kilometers, maybe it's 1 centimeter, I don't know. But whenever you plug in those values, right, then you multiply by that constant, okay, which I told you is a small number. It ends up being almost a trillionth, right, in terms of its standard order of magnitude using standard units, on the order of 10 to the negative 11, right? But usually because masses of things like planets and moons are so big, right, they're trillions upon trillions of kilograms, so you end up, with a fairly big number here, and that's going to be your actual force in what units? Newtons, okay, which is the units we always measure force in. So what's interesting is it's just another force equation, kind of like F equals ma, or force pairs, right? F1 equals F2, force on one equals the force on two, right? Or even the idea that if force is zero, then velocity can't change, right? All the forces we've seen before, everything we do, we're always in newtons. That was always the the base unit to use. Same thing here, right? Because all this universal gravitational law tells us, right? The law of universal gravitation, it just tells us where a force comes from. Right? It doesn't tell us what all the forces come from, including a discussion of electricity and magnetism is going to help fill in some big gaps in our understanding, but it tells us where one fundamental force comes from, okay? Or at least how that force functions, because modern physics begs the question of, well, what really makes gravity, right? Is there a gravitational particle? And we actually don't know, okay? But all that aside, okay, what we do know is we know that it follows this form, okay? All right? On the large scale, on the macroscopic scale. Right, so this leads to the idea of satellites. If we think about the moon's motion around the sun, that leads to the different phases. So phases are just a direct consequence of all of this circular motion, right? The fact that Earth is not staying in place, that the moon isn't staying in place, right front and center, phases of the moon. All right, so is it possible to see the moon in this orientation, right, as a crescent moon? No, right, because there's never going to be stars between the Earth and the moon like this, right? Because the fact that the moon is so much brighter, you would never see stars that close to the moon, right? So let's take a look at the numerical example. Okay, all right. So I want to just start off without the numerical example. To be honest, I want to show you Kepler's third law combined with Newton's law of universal gravitation, also sometimes known as just the law of universal gravitation. Okay, what do I mean by that? Check it out. Okay, so we'll go over here. All right, so don't need to see any equations. I just want us to consider Earth represented as M2. Of course, that's going to be in the universal gravitational formula. All right, and some satellite, maybe like a transmission satellite, TV satellite, M1. Okay. That satellite has some velocity. We know it has to have a velocity because that's how it maintains its orbit, right? That's how it's managing to fall around Earth but never hit it, okay? So then we've got Kepler's third law. A proportionality, not an equation. Well, let's fix that, okay? So we're then going to consider the universal law of gravitation, okay? So that is just some force here. I put a subscript to say that it's the force of gravity, just because I'm going to compare it to another force. All right, and this is its exact form as proposed by Newton, right, which turned out to be absolutely correct, right, for basically things that aren't black holes and aren't the Big Bang, these extreme cases of gravity. This works very, very good for planetary gravity. All right. Okay, so this force is a centripetal force. This is a big idea I talked about in the previous lecture for the first half of this chapter, that centripetal force is always created by some other force. Gravity can be one for sure. Well, here it is. Here's the gravitational force expressed correctly in its form, right? And it's a universal form representing the centripetal force, playing the role of the centripetal force. How so? Because it's maintaining the circular orbit of the satellite. By the way, keep things simple. It's not. We don't want it to be an elliptical orbit. We could, but it's better to start as a circle. That's perfectly a good way to consider this. Okay. So now what do I have? Well, if the gravitational force is equal to the centripetal force, that's literally just saying that this expression here is equal to the centripetal force, which we know from the previous video for this chapter is just mv squared over r. Okay? That's just m times the centripetal acceleration, and the centripetal acceleration is precisely v squared over r. Okay, so why have I done this? Well, because I want to show something. I want to simplify this expression. Right away, the mass of the satellite cancels out. Okay, interesting. I can continue to simplify it because I've got some r's over here and an r over here, right? Since both the r squared and the r are in the denominator, they can cancel each other out, but they can't exactly because one's an r squared and one's an r, but the r squared can become just an r on its own, and this r is just completely gone because it canceled with the square, because r squared is r times r, right? So essentially, an r times r, we canceled one of them. Okay? Can we clean up any more? Not yet, but we have a kind of interesting thing here, right? By just acknowledging that the gravitational force, the universal gravitational force, is a centripetal force, we've got this relationship now between the mass and the radius, that constant, and the velocity squared. Is that useful? Absolutely. Because what does it mean to have a circular orbit, right? Well, a circular orbit means that your velocity isn't changing. Well, if your velocity isn't changing, then there's a really simple way to relate velocity to distance over time. Because constant velocity is always distance over time, okay? If I'm running at a constant velocity down a racetrack that's 100 meters long, and I do it in 1 minute, then my constant velocity over that entire 100 meters is just 100 meters divided by 60 seconds, right? If I wanted the meters per second, the standard. Well, do the same thing here. Because you know the entire length of the orbit, it's just the circumference of whatever, depending on whatever the radius is, it's just 2 pi r. That's literally the circumference of a circle. And the time it takes to do it is t, the orbital period. Well now look at that. Now we've got everything that was in Kepler's third law, period and orbital radius, right? Orbital period and orbital radius. We've got those now in the same equation because we're going to substitute this Vn, make sure to square it, see? Make sure to square it, and then deal with the squared, right? Actually bring the squared in and square a bunch of stuff. So the 2 pi becomes 4 pi squared. The r just becomes r squared because I'm just squaring each term. And then the t in the denominator becomes t squared. Now we can actually clean it up even more. And what do we get? Kepler's third law. Okay? So there is as a proportionality. There it is as an equation. They're actually both called Kepler's third law. This version, okay, this equation version with all the constants that we need, all right, we can actually plug in numbers. This one is often called Newton's synthesis of Kepler's third law. Okay, so pretty cool, right? Got a new equation by just combining two other ones. Okay, so now, as promised, let's plug in a couple numbers with two quick examples. Okay, so come over here. All right, just want to just keep this up so we can kind of have a picture to refer to. So in the first one, I want to just come up with a relationship for the force between them, okay? So just how much force is there between these two objects? So example 1. All right, so what is the force between, it's the gravitational force, m1 and m2. Okay, now what are the values, right? So you have all the values you need, which are going to be that m1 is the mass of the satellite. I'm going to give that as 6,000 kilograms. m2 is going to be the mass of the Earth. That's going to be 6 times 10 to the 24, this is a pretty accurate number, rounded a bit, kilograms. So it's basically 6 trillion, because a trillion is 10 to the 12, so 10 to the 24 is a trillion trillions. So how many kilograms are in the entire Earth? The other value you're going to need is going to be the radius, okay? So this isn't, this is just some arbitrary satellite. I'm going to put it pretty far away. I'm going to put it at, let's do it at 2,000 kilometers, right? So 2,000 kilometers, you probably want that in meters, but I'll leave it in kilometers for now, okay? So 2,000 kilometers. And then g, which I've been hinting at, that is the gravitational constant, is 6.67 times 10 to the negative 11 units on it, which are the units necessary for both sides of the equation to match up not just numerically, but also dimensionally, which is to say the same units, are newtons meters squared over kilograms squared. Okay, so pause now if you want to remember the equation or see if you can, or look it up and go from there. Otherwise, I'm going to give you the equation. Okay, so now time for the equation. The equation that we will need is the universal gravitation equation, which is G m1 m2 over r squared. Okay, so that's what we want to plug in. We want to make sure all of your units are in base units. So far, I gave them all to you in base units, except for the radius, the orbital radius of the satellite. Okay, that you need to convert over to meters. Okay, gravitational constant is good to go. It's in the correct base units, newtons, base units, right? In a sense, newtons are built on base units. It's called a derived unit, but it's all built on kilograms, meters, and seconds. And then everything else you see are just meters and kilograms. Okay, so the only thing you have to convert is the radius. Okay, all right. So give that a try, and then I'm going to start plugging the values into Desmos. Okay, see if you can get a number that you feel confident about. Gravitational force between this satellite and this, Earth, this planet. Okay, so I'm gonna start plugging them in. I'll just call this F. Okay, and then we'll plug in our 6.67 times 10 to the negative 11. I'll often save this as a constant ahead of time and just refer to it in Desmos, but we're just doing one calculation here, so it's not necessary. And then M1 and M2, all right, so 6,000. And then times 6 times 10 to the 24. So make sure you're good on entering all these equations, all the scientific notation. I'm then going to divide the whole thing because I want it to kind of look like the same form here. If you just had the division on any one of those terms, that's fine. PEMDAS allows it, but I like my equations to look similar to the actual formulas, so I know I'm doing everything correctly. And then I have my 2,000, and then I'm just going to multiply by 10 to the 3. Because that is the conversion from kilometers to meters. So now I'm done converting. Don't forget to square. And we end up with a force, all right, of 600,000 newtons. So it'd be 6, because we wouldn't record the 3. It's too off from our significant figures, which we're really kind of working with 1 or 2 at most. So I'll say 2. So 6.0 times 10 to the 5 newtons. Okay? All right. So that is actually the gravitational force between the satellite and the Earth. Okay, how does that compare to the gravitational force between a person and the Earth? It's bigger, right? Because the satellite's massive. But the fact that it's pretty far away does matter. All right. And one thing is we included, actually interestingly, I want to fix the radius here because I included, oh no, that was fine. That was from the, but that wouldn't make sense, okay? Because I was thinking 2,000 being the distance from Earth, right? Or from the surface. Now, but that doesn't include Earth's radius. Sorry for overlooking that. But Earth's radius, right? If we're to I'll zoom in here, has a value of 6,000. So you can see numerically why, it wouldn't work to have 2,000. So I'll put this in a color we can see a bit better. This might actually should show up there. Okay, so this value right here, which I'll just call RE, okay, well, RE is 6,300 kilometers, okay? So if I was thinking 2,000 being the extra distance, which the arrow doesn't quite imply, because when I first drew the figure, I wasn't worrying about that. R is just some distance. So R is the the distance from the surface of the Earth up until the altitude of the satellite. Well, in this case, if it's only 2,000, the figure's certainly not drawn to scale. So let's make it a bit bigger. How about let's make it a much higher satellite, which are often the kind that are known as geocentric. So I'm going to change the value and change the calculation over in Desmos, something that kind of matches the figure, which is 20,000 kilometers, right? So that means that R is, it's bigger, right? It's only about 3 times bigger, so still not quite to scale with the figure, but certainly that it is larger, right? It's over 3 Earth radii from the center of Earth, right? And that's the only number we need, because the number you plug into the universal law of gravitation isn't the altitude of the satellite, it's the distance from the center of the planet and the center of the satellite. Okay, so it's the center to center distance. And so that's the R that I'm giving you here, the updated one, 20,000, and that is a center to center measurement. okay, as it should be in the universal law of gravitation. So we'll fix that number over here, okay, and just add a 0. All right, so now we have our 20,000, still converting it over to meters. That's going to correct our force significantly, and we'll end up with 6,000 newtons. And this is kind of cool because having this satellite this far away, I think, is a good demonstration of how the gravitational force does decrease of distance. It doesn't, go away, but it decreases, right? Because 6,000 newtons is actually comparable to something that only weighs 1,000 kilograms here on the surface of Earth, right? Because if you think of, it would be, you multiply by 10, so if you divide this by 10, so 600 kilograms, even less than 1,000. So something that weighs 600 kilograms would give you this weight on the surface of Earth. How much does this thing weigh? Certainly not 600, 6,000, right? So it's it would be a lot heavier if it was actually sitting on the surface. It's effectively not as heavy as a satellite. Why is that? What does that mean? Well, that means that if the satellite was to stop moving, right? If it was suddenly going to stop moving, if it lost its velocity, well, then it wouldn't be a satellite anymore. It wouldn't be falling and moving to the side fast enough to be a satellite. It'd lose its moving to the side part, right? So it would just fall straight down, okay? Now, it wouldn't fall at 10 meters per second squared or 9.8 meters per second squared more accurately. It would fall at some slower rate. What would that rate be, right? So in question B, what would be the acceleration of the satellite, all right, if it was to stop moving? So what would be the gravitational acceleration of the satellite towards Earth? Okay? Because technically it actually has that acceleration. That is its centripetal acceleration. It just doesn't pull it towards Earth because it's moving to the side. That centripetal acceleration is completely being used up, if you will, to turn it. But if it was to lose its velocity, lose its kinetic energy, as we'll talk about in a future chapter, it would just fall straight down, as I said. Okay, and that's what this number could represent. Okay, so what would be the gravitational acceleration of the satellite towards Earth? Okay, so think if you know how to solve this. Pause if you want to remember. Connect the dots how to solve it. It's something you saw in chapter 4 when we saw Newton's universal laws. Well, Newton's laws of motion, not his universal law of gravity. Just call it Newton's laws of motion, the 3 of them. Okay. Well, you want F equals ma. Okay. Simply. Because think what you have. You know what F is. There's only one force acting on the satellite. Okay. There's no drag in space. There's no other forces. The only force acting on the satellite is none other than the force of gravity. Okay, and the force of gravity, as I pointed out in my kind of previous example / derivation on the previous page, is just equal to the centripetal acceleration. It is the centripetal acceleration. Okay, or rather, the gravitational force is the centripetal force. Okay, it's playing that role. So, and it's the only force, so it's also F net. Okay, so because technically Newton's second law isn't just F, that's not just some force, it's the total force, F net, F total, right? And in this case, F total is just Fg, okay, which is just ma. So if we know what Fg is, then we can just solve for A. So we plug in our value of 6,000 newtons, right, the only force acting on the satellite, plug in its mass of 6,000 kilograms. That's convenient, isn't it, right? And then that just worked out that way, by the way. It's a happy coincidence, right? And then multiply by A, right, because A is our unknown. That's what we're solving for. Well, then if we just solve for A, we get that it's going to be 1 meters per second squared. Okay, so just to show that it's approximately 1, but not doing any rounding. Over here, I'm just going to take F, right? Also seeing how you can just take saved variables in Desmos, and I'm just going to divide it by the exact mass of 6,000. Okay, and there we go. So it's 1.0005. Yeah, so definitely round as a 1. Okay, so. Is that weaker than the gravitational acceleration that everything shares on the surface of Earth? Sure. That's because we're much further from Earth, okay? That also dictates what the velocity of the satellite would look like if we wanted it to actually maintain a stable circular orbit, okay? And it shows that gravity gets weaker of distance, right? Because if we aren't worried about things, maintaining stable orbits, then what we were thinking about is two bodies floating in space gradually getting attracted to each other. And if that was the case, if this was deep space and these are just two objects at rest, then they would start accelerating towards each other. At first, not that quickly, right? But of course that rate would speed up as they got closer, okay? So we see that the acceleration, just like the force, is dependent on the distance. And it also falls off precisely to the square of distance, right? It is also proportional to the inverse of the square of distance, because acceleration is directly proportional to force. So what force does, so does acceleration. Okay? Now the last thing I could ask you for, but I won't, so you can just do it on your own, is to calculate something like the period. Okay? Because that's just the last thing that you would do, is you would say, okay, well, I know, how much force is acting on the satellite. I know what its acceleration is, which is its centripetal acceleration. All right? So really the last question is, what is its period of orbit? Okay? And by the way, just to be, remind us that is in fact the centripetal acceleration, not just this imaginary free fall acceleration. And so, as I said, the last question, which you can try on your own, would just be, what is the period of the satellite's orbit? That's t. So now you'd be using Kepler's third law, but Newton's version of it. So what is the period t of the satellite's orbit? All right, so try that one at home. Okay, so that concludes chapter, which one? 5? Yeah, 5, chapter 5, right? Where we talked about circular motion and orbits. Okay, I hope this lecture, as well as the previous one, have been interesting and informative. Thank you so much for watching.